Stack application. Stack is among the most widely used data structures. It also forms the basis of other complex and advanced data structures. Stacks are extensively used in a host of computer applications. They play a central role in program compilation and translation of high-level languages. The fundamental compilation processes, such as checking the syntax of statements and conversion of arithmetic expression for evaluation by the computer, rely heavily on the use of stacks. Stacks also play a crucial role in the implementation of subroutines and function calls. Stacks are indispensable in coding of recursive procedures. Many search algorithms employ stacks to backtrack to previous states. Stacks find common use in several computer applications such as text editors, web browsers, and image manipulation softwares. Now we examine in some detail the use of stack for parsing of arithmetic expressions and their evaluation by the computer. Later, we shall briefly review some other applications. Using stack for parenthesis matching. Parentheses are often used in arithmetic expressions to specify the priority of evaluation. A pair of parentheses is also used in some programming languages, such as Fortran and BASIC, to enclose index of a dimensional variable. In a syntactically valid expression, each left parenthesis must match with the corresponding right parenthesis. A simple counting of left and right parentheses would not provide a correct solution. For example, this expression has same number of left and right parentheses, but it is obviously illegal. We can use a stack to validate an expression by checking that for each left parenthesis there is a right parenthesis in the correct position. Here is the algorithm. Number 1. Scan the expression from left to right. Number 2. If a left parenthesis is encountered, push it onto the stack. Number 3. When a right parenthesis is found, pop the stack. If stack is empty, report a mismatched right parenthesis. Otherwise, pop the stack and discard popped left parenthesis. Number 4. At the end of scan, if stack is not empty, report an error. This algorithm can also be used for matching other symbols such as curly braces and square brackets. Recall, braces are used in Java and C, C++ to enclose a group of statements. Conversion of infix expression to postfix notation. We now examine how a stack is used by the computer to evaluate an arithmetic expression. In a high-level language, an arithmetic expression consists of variables and constants called operands and symbols for arithmetic operations. By convention, these operations have the following order of precedence. Number 1. Exponentiations are performed first. Number 2. Division and multiplication are performed next. Number 3. Addition and subtraction are performed last. Number 4. When two operators of the same precedence appear consecutively, evaluation takes from left to right. Number 5. Parentheses may be used to enhance the level of precedence. Examples of simple arithmetic expressions are a plus b, a minus b, a static b, a slash b, and so on. The algebraic notation for arithmetic expression is called infix notation. In this notation, an operator is placed between a pair of operands. The infix notation is not suitable for computer evaluation. To simplify the processing steps, two alternative representations are used, which are called prefix and postfix notation. In the prefix notation, the operator symbol is placed before the operands. For example, the infix expressions are written in prefix notations as shown. The prefix representation is also called Polish notation in honor to its inventor, Polish mathematician John Lukowicz. A complex arithmetic expression can be converted to prefix notation by processing the brackets and operators in order of their priority. For convenience, square brackets may be used to indicate partial conversions. Here is an example. In another notation called postfix or reverse Polish notation, the operator symbol is placed after the operands. For example, the infix expressions are written in postfix notations as with the prefix representation, the infix expression can be converted step by step by partially converting the operators and brackets according to their precedence. For example, this infix expression is translated to postfix as follows. Notice that postfix expression has following features. Number 1. All operands have the same order as in the infix expression. Number 2. Parentheses are not required. Number 3. Postfix expression is not the reverse of its equivalent prefix expression. Visual conversion of infix expression to postfix notation is awkward and prone to errors. A better way is to use stack for intermediate or partial conversion. To this end, we can use an algorithm which is based on the observation that in postfix expression the operators maintain their order and that operators of higher precedence should be evaluated first. Also, since left and right parentheses are not required in the postfix representation, these should be discarded after partial processing. The conversion algorithm consists of following steps. Number 1. Scan the infix expression from left to right. Number 2. When an operand is encountered, append it to the output string for postfix representation. Number 3. Push each left parenthesis onto the stack. Number 4. When an operator is encountered, check if stack is empty. If so, push it onto the stack. Otherwise, pop operator of the greater or equal precedence from the stack and append it to the postfix output string. Continue popping until either left parenthesis is encountered or an operator of lower precedence is at the top or stack is empty. Number 5. When right parenthesis is encountered, pop off the stack and append the popped operator to the end of output string. Continue with this process until a matching left parenthesis is encountered, which should also be popped and discarded. Push the new operator onto stack. Number 6. When the scanning process is complete, pop off all operators from stack and append them to the output string. The algorithm appears to be overwhelming for manual conversions. It is, however, better suited for machine conversion. To understand the working of algorithm, consider the conversion of following infix expression. In this expression, caret symbol indicates exponentiation. The conversion steps are as shown on screen. Notice that up to step 8, all operands are appended to the output and operators are pushed onto stack. At step 9, right parenthesis is encountered and as consequence, minus and left parenthesis are popped. The minus operator is popped and left parenthesis is discarded. At step 10, slash is encountered. As a result, asterisk, which has the same priority as slash, is popped and appended to the output, and slash is pushed to the stack. At step 12, plus is encountered, which has lower priority than slash in the stack. Thus, slash and plus of equal priority are popped and appended to the output, and new plus is pushed to the stack. At step 14, caret is encountered, which has higher priority than plus in the stack. It is therefore pushed to the stack. At step 15, the scanning of infix expression is complete, and therefore plus, caret, currently in stack are popped off and appended to the output. In this way, the infix expression is converted to postfix expression. Evaluation of arithmetic expression using stack. We have stated before that arithmetic expressions in algebraic notation are not suitable for evaluation by the computer. Generally, an expression in infix representation is evaluated in 2 steps. First, it is converted into an equivalent postfix expression by using the algorithm previously explained. Next, the variables in the postfix expressions are replaced by their current values. Finally, the postfix expressions with numerical operands is evaluated. The last evaluation is carried out using stack to save the intermediate results. The algorithm for computation involves following steps. Number 1. The arithmetic expression in postfix notation is scanned from left to right. Number 2. If a numeral is encountered, it is pushed onto the stack. Number 3. If an operator is encountered, 2 operands are popped off the stack and the current operators is applied to the operands. Number 4. The result is pushed onto the stack. Consider, for example, the infix arithmetic expression. In postfix notation, it is written as: using the previous evaluation algorithm, the postfix expression is processed. The evaluation steps are depicted in figure. Use of stack in function calls. A stack plays a pivotal role in the execution of function calls. When a function is invoked, program control is transferred to entry address of the called function. After the function has been executed, the control is transferred to the next instruction in the calling program. The function calls can be nested, which means that a function can, in turn, call another function. In this process, the system must remember the addresses where to backtrack after the call function has been executed. Therefore, the return addresses and the local variables must be saved and retrieved in the reverse order. This task can be performed most efficiently with the aid of a stack. When a program or function calls another function, its arguments, the return address, and values held by the local variables are pushed onto the stack. After the call function is executed, the saved data is popped off the stack and control is transferred to the popped address. A data structure that holds the function parameters, local variables, and the return address is commonly known as stack frame. Almost all compilers for high-level programming languages make use of stack frames to process function and subroutine calls. An example of function calls and working of stack frame is shown in the figure. The function main calls a function alpha. The function alpha in turn invokes function beta. After beta has executed, the control is transferred back to alpha. When alpha has been executed, the control is transferred to main. At each stage, the value passed as arguments to the function, its address, and values of local variables are preserved in the stack frames. On backtracking, these are popped off the stack frames and returned to the calling function. Use of stack in recursive procedures. A procedure in which a function calls itself is called recursion. It is a powerful technique which is extensively used in concise description or solution of a problem. For a recursive procedure to be useful, it must satisfy two conditions. First, each procedure call should bring it closer to the solution. Second, there must be a decision point at which the procedure should terminate. A recursive procedure that satisfies these conditions is said to be well defined. Since a recursive procedure is generally implemented in 3 steps, which are known as prologue, body, and epilogue. In the prologue step, the function arguments, local variables, and return addresses are saved by pushing them onto a stack. In the body step, a base criteria is used to determine whether or not the recursion should terminate. If so, the epilogue step is initiated. Otherwise, some processing or computation is performed and prologue step is invoked again. In the epilogue step, saved parameters, local variables, and addresses are popped off the stack and used to perform the intermediate computations. A simple example of a recursive procedure is the evaluation of a factorial. You would recall that the product of successive positive integers is called factorial. Consider, for example, the evaluation of the function factorial of n. If n equals 4, the recursive steps would be as: by backtracking the above steps, we can obtain the value of factorial of 4. An example of C++ function that can be called recursively to compute factorial of a given number is as shown. Use of stack in application software. Stacks are commonly used in the implementation of several application packages. Current generation of desktop applications such as word processing, spreadsheets, graphics, and image processing include feature to cancel any previous processing steps. In word processing, for example, any changes to a currently open document are pushed onto the stack. When the undo option is exercised, the changes are popped off the stack and applied to the current version to revert to the old version of the document. The web browser frequently uses stack to maintain a history of visited sites or downloaded web pages. As the web pages arrive, they are pushed onto the stack. Later, if a user clicks the back button, the stack is popped off to display the most recently downloaded page. In the same way, the browser can retrieve the most recently visited sites. Stack machines. Because of their frequent use in several computer science disciplines such as compilers, interpreters, and operating systems, stacks are increasingly being implemented in the hardware architecture. Originally, this facility was built into mini-computers such as PDP-2 and Burrow 5000. For this reason, these computers were commonly referred to as stack machines. Currently, most CPUs, such as Intel and Motorola processors, have built-in features for stack. The instruction set for these processors include push and pop mechanism. A push instruction causes the contents of specified memory location to be saved in the stack register. The pop instruction removes the top entry in the stack register and places in the main memory.